Hi guys, thanks for tuning in to my second video about how to divide your school into cohorts for a hybrid or blended learning model. If you missed my first video, I'll put a link in the description below. If you did watch my first video, then you'll remember that our goal is to divide our school into cohorts in a way that prevents an undesirable imbalance between the size of the two groups. The example I used last time was a first period math class and a first period biology class, each of which was divided into an A cohort and a B cohort. And the way that we've divided these, at least during first hour, we have two cohorts of equal size in all of our classrooms, so it's possible to maintain physical distancing. However, if we're not careful with how we assign students to these cohorts, we're likely to end up with some classes that have an excess of A's and no B's, or vice versa, which would make physical distancing impossible. On the other hand, if we use more advanced techniques to assign students to our cohorts, then we could try to make sure that physical distancing is possible in every single classroom throughout the day. In this video, I'm going to demo a program that uses a genetic algorithm to examine thousands or even millions of potential schedules as it works its way towards an optimal solution. Now you can install this program by going to GitHub. Let me open up my GitHub repository right here. I'll put a link to this repository in the description below. But for the remainder of this video, my goal is to help you get started with this program by walking you through the process of installing and running this software and explaining how the different pieces work. And before I go any further, I'd also like to acknowledge my co-authors, Jerry, Alice, and Eileen. Without their hard work, this program would be nowhere nearly as efficient or as easy to use as it is now. So once you've landed on this GitHub repository, if you are familiar with GitHub, you can of course just clone this repository. But for most users, you'll probably want to go to the Releases tab here on the right-hand side and click on this Student Partition Optimization tool. Before you click on that, you might notice that there is a lot of documentation, and it is worth reading through that documentation because that information will just supplement what's in this video. So when you click on this release, you're going to be brought to a zip file that you're going to want to download. Now it is 283 megabytes, so it is going to take a little while to download, and so you didn't have to sit around and watch it download on my computer. I've already downloaded this, and I'm going to extract it for you guys. Now once the zip file is done extracting, which only takes a couple seconds, I should mention the reason that this file is 283 megabytes is there is an executable here, a Windows exe, that you can launch this program from. And what's nice about it is you don't have to have Python installed. You don't have to make sure you have all the correct modules installed on your computer. You can just run everything from this exe file. Now it does give you a little less flexibility when you want to modify the program to meet your school's needs. So if you want to just experiment with the exe file and then move on to the actual Python file that you can make modifications in, that's a really good option for a lot of schools. Or if you just want to use an out-of-the-box version of this program, the exe file will be fine. Now I'm not going to double-click it right now because it does take a little while to load. It's basically installing Python and all of the modules you need when you launch the program. So instead, I'm going to launch this program from the command line. And that's probably how a lot of users will want to launch this program. And you get a nice little graphical interface here. Let me explain all the different parts. So partition size is whether you want to divide your student body up into 2 cohorts or 4 cohorts. Basically, are students going to school 50% of the time, or are they going to school 25% of the time? For this example, I'm going to put 2 here because we're going to divide the student body into an A cohort and a B cohort. Max class size, 2 groups. This next entry is your desired maximum size for a particular class when you've divided into a 50-50 split. What I mean by that is, let's say that most classes in your school have 30 students in them. And let's say that you've brought a tape measure into your typical classroom and you've realized that to maintain physical distancing, you can't have more than, say, 14 students in the room. Then you would want to change that number to 14. So the idea would be that you're trying to keep groups of about 14 in your A group and about 14 in your B group. And the program will try to work towards this as best it can. Now at the max class size for 4 groups, this would be if you're dividing your student body into 4 cohorts. This is the maximum size of a class when you have a 25%, 25%, 25%, 25% split between your A, B, C, and D cohorts. If you put 2 up here, this number is going to be ignored, so you could just leave it as 9 if you'd like. Next, we've got student course data. The first time that you run this program, you'll probably just want to select the example student data, and for required student subgroups, you'll probably just want to select the example subgroups file. And then you'll want to leave preferred student subgroups blank. But before we go any further, I should probably show you what kind of data is in each of these CSV files. So let's open up example student data first, because that'll give you an idea of what kind of report you're going to have to run at your own school to be able to run this program on your school's data. So this is just a very simple CSV report that has a row for each class that each student is taking at this school. So for example, we have this student Aiden Abbott, and Aiden is taking 5 classes. So Aiden is taking up 5 rows of this CSV report. Now, the most important columns in this CSV file are student ID, room number, and period. That's because this program is going to uniquely identify students by their ID number, and it's going to uniquely identify classes by the room the class takes place in and the period in which it takes place. So everything else here is somewhat optional because you can easily modify the Python script to get rid of something that you don't need. For example, if you don't care about middle initials, you can modify the program. What is not optional, though, is you can't modify this program to ignore student ID numbers, room numbers, or periods because those are our unique identifiers. Now, this example data is very similar to a report that you can generate in Infinite Campus if your school uses that particular student information system. And I would guess that a lot of other student information systems can generate very similar reports. The important thing being that we have a row for each class that each student is taking at the school. Next, let's talk about required student subgroups. So let me open up required student subgroups. And this is a much simpler CSV file. This is basically a list of pairings. So we have ID numbers for an initial student and an ID number for a second student. These 2 students are part of a subgroup. So the student with the ID number 563 and the student with the ID number 1223 have to be assigned to the same subgroup together. Basically what that means is it's likely that these 2 students are siblings, and we want to make sure that they're either both in the A cohort together or both in the B cohort together. Now it's actually possible, like let's say that student 563 and student 1223 have another sibling that appears somewhere else in this spreadsheet. If we have, let's say we had another entry that was 563 and 1871. What this would mean is that student 563, student 1223, and student 1871 all have to be assigned to the same cohort together because they're all siblings. You don't have to have sibling pairings, by the way. Of course, you can have subgroups for other reasons. For example, let's say you have an ELL class where you have a small group of students that all speak the same language and you want to make sure that they're all in the A cohort together or all in the B cohort together. They can be in this spreadsheet as well, though I will say from an Infinite Campus perspective, it is really easy to export a report of student IDs with sibling pairings, and it's if you're doing something that's more complicated than sibling pairings, you would probably have to input these ID numbers manually into the CSV file. Once you have gotten all of your student subgroup requirements together, then you would upload that spreadsheet to the program. Now what I am going to point out here is the example data is for a school of about 3,000 students, and right here my required subgroups involve 1,300 different requirements. That's to say that, suppose that the school has about 1,300 sibling pairings for a population of 3,000 students. You can make this even more restrictive if you'd like. You can go way above 1,300 students for your subgroups, but the more students you add to subgroups, to required subgroups, the more difficult it will be for the program to optimize. So what you would not want to do is say, okay, all the siblings should be together. We have this other set of requirements that these students should be together, and here's some more requirements. If this spreadsheet gets way too large compared to the size of your student body, the program's not going to be able to find a very optimal solution for you. So you want to keep this limited to student pairings plus maybe some other small requirements, but not much more beyond that. For preferred student subgroups, that spreadsheet would look exactly the same in terms of formatting as required student subgroups. The difference here is how the program is going to treat these subgroupings. Required student subgroups have to be assigned to the same cohort. So this would be to say, at our particular school, we must assign siblings to the same cohort. Those would be required subgroups. Preferred subgroups would be pairings of students that it would be nice if they're together, but they don't have to be. And the program will try to put those students together, but it's not a guarantee. And then finally, we have max runtime, the number of minutes that this program is going to run for. By default, it's going to run for 8 hours, 480 minutes. However, for my example here, I'm going to go with 2 minutes because I don't think you're going to want to watch this program run for 480 minutes. My recommendation is that when you are running this on actual data rather than example data, you probably are going to want to let the program run for at least 8 hours, if not more, depending on your school's needs and the size of the school and the complexity of the subgroups that you've uploaded. Once you have all of these settings, you can click Start Partition Optimizer. And let me get the command line view and the graphical interface together so you could see them both at once. So we could see the fitness score here of our population generally increasing over time. Now, each of these lines that you see in the command line represents a generation in our genetic algorithm. And if you let this run over the course of 8 or 16 or 24 hours, you're going to go through thousands or even millions of generations working your way towards an optimal solution. After a few minutes, you're going to get some visualizations that will pop up that will continue to update as the program runs. This pie chart is basically a representation of the courses at the school that are currently in compliance with your physical distancing needs and the courses that are out of compliance. In compliance would be classrooms where you have 15 or fewer A's and 15 or fewer B's. Out of compliance courses, for example, could be a course where you say have 20 A's and only 3 B's. That course would be out of compliance. And as the algorithm runs, what you'll notice is that this out of compliant wedge is going to get smaller and generally get smaller over time. And the in compliance wedge is going to get larger. And at least with the example data, if you run this for a good 8 hours, you can get it to about 590 classes that are in compliance compared to only 12 sections that are still out of compliance. And then if you look at this histogram right here, this is a measurement of how much the classes that are out of compliance deviate from a 50-50 split. So what you'll see right here with this with the histogram here with this 0.20, these are the courses that deviate from a 50-50 split by 20% or more. So you have about 5-6 classes at the school at this time that have a 70-30 split between the A group and the B group, or vice versa. When the program finishes running, usually this will be many, many hours rather than just 2 minutes. You can click this button to open the folder that has the reports that the program generates. There are 2 reports that you're going to get. The first report is really simple, student assignments. Let's open up that one because it's the easiest to discuss. All it is are it's student ID numbers, the name of the student, and which cohort the student has been assigned to, either in this case the A group or the B group. So you can use this report to communicate to students which cohort they've been assigned to. And then we have a second report that's a little bit more interesting, and that's a course analysis. This course analysis, when it loads, is going to be helpful for figuring out which classes still have some problems. Now, what I like to do is I like to go through the CSV file in Microsoft Excel. It's going to take me a little while to highlight all this data, but once we have this all highlighted here, we have 602 sections, so 602 rows of data here. And I'm going to format this as a table. And the reason it's nice to format as a table is it's really fast to sort our data here. So I'm going to sort by max deviation and in compliance. And what that'll give us, here's a list of all of our courses that are still out of compliance. And then there's some information here where you could try to figure out why the course is out of compliance and how badly out of compliance it is. So again, let me explain this concept of out of compliance. So let's look at this, the most egregiously offending course at this school at the moment. We have a max deviation of 22%, and we have an A count of 21 and a B count of 8. So basically what's happening here is we have assigned 21 students to the A group and 8 students to the B group in this particular course, which is not very good. And so this max deviation is saying that we are 22% away from a 50-50 split between the A group and the B group. Now this shouldn't be very surprising because the program only ran for 2 minutes. If you run the program for a good 8 hours or more, you're going to notice that there are going to be very few courses that are not in compliance. And when you look at these max deviations, they should be fairly small. You might look and say, oh, well, yes, technically this course is out of compliance, but we have 17 A's and 14 B's, that's not so bad. Or, oh, this class is only one student away from being in compliance. We can go into our master schedule, make this small change in the student schedule, and now this course will be in compliance. So this report should be fairly helpful with making a few manual changes to fix any remaining problems in your school's schedule, though there shouldn't be too many of those left after you've run the program for long enough. After you've run the algorithm on your school's data, then you can start experimenting. And so I don't want to go into too much detail here because I don't want to get too technical, but if you were to open spots.py, there's a particular place that your school might want to edit the code so that the logic matches with your school's particular needs. So this file is fairly thoroughly documented. So hopefully that will be helpful as you work through this source code here. But what we're looking for is the schedule class and a particular method in the schedule class, basically our fitness function. So let me scroll down till we find it. Here it is, fitness score. So this particular method is only a couple hundred lines of code, but it governs the core logic of this algorithm. So this is the function or the method that tells the genetic algorithm whether a particular assignment of A's and B's is acceptable or unacceptable. And so this is what you would want to modify if your school has needs that are different than what I demoed in this program. So for example, right here, it says if number of partitions equals 2. So if we're trying to divide our students into a 50-50 split between A's and B's, and then we have basically just some conditional logic here that determines whether, how many A's and how many B's are allowed in each classroom for it to be acceptable. You could do some slight modifications here. It's only a couple hundred lines of code, and the program will adapt to those changes, and you'll be able to adapt this program to the needs of your school. And that's basically all I have. So I hope that this was a helpful demo. If there's anything else that you guys would like me to demo in a video, please let me know in the comments below or send me an email. My email address for this project is in the README in my GitHub repository, so feel free to get in touch. And good luck with the coming school year. Thanks for tuning in.